Hello, everybody. Today we're going to go over section 4.2 on ranking data. A test score in and of itself is usually difficult to interpret. For example, if you learned that your score on a measure of shyness was 35 out of a possible 50, you do not have the context to interpret that result. Most people ask next, how does that compare to other people's scores? We standardize this idea with the percentile rank, the percentage of people who scored lower than you on some assessment. If 65% of the scores were below yours, then your score would be the 65th percentile. Your own percentile rank is an easy to understand statistic measuring the relative position of your score within the distribution. However, using a list of 100 different values is too cumbersome to be able to analyze the distribution as a whole. Instead, let's divide the distribution into a smaller, more manageable number of categories. Start by splitting a distribution in half. To do so, we identified the median of the distribution, a score that marks the 50th percentile. By definition, half of the data in a distribution is lower than the median, and half of the data is higher than the median. When a distribution has an odd number of elements, the median will have a value of a score in the distribution. For example, in the small distribution 3, 4, 5, 6, 7, 8, 9, the median is 6 because it has 3 scores below it and 3 scores above it. If a distribution has an even number of elements, the median may not actually be a score in the distribution. For example, in the small distribution 1, 3, 5, 7, 9, 11, the median should be somewhere between the 5 and the 7. 3 in the first half, 3 in the second half, 5 and 7 as the end point of the first half and the beginning point of the second half. So right in between the 5 and the 7, halfway would be the average of the two. 5 plus 7 is 12, divided by 2 is 6. And you might have been able to tell that 6 would be halfway between 5 and 7. Anyway, we say that the median of this distribution is 6. When a distribution has a large number of scores in it, calculating anything by hand can be frustrating. However, if the distribution can be presented nicely, there are some tricks we can use to make the calculation manageable. To see how, let us return to the sample of mall shoppers that we studied in the last section. So example 1, shoppers at a local mall were polled to find out how many stores they planned to visit during their trip. The results are shown in the table below. Determine the median of this distribution. So our first column is the number of stores they plan to visit during their trip. The second column is the frequency that result came up. In other words, 3 people said they were visiting 1 store, 5 people said they were visiting 2 stores, 7 people said they were visiting 3 stores, so on and so forth. Our 4-step problem-solving process returns. It will never go away. Step 1, understand the problem. We have a frequency table of data, and we want to calculate the median. Step 2, devise a plan. The median is the middle score in a distribution. If we know how many total elements are in the distribution, we can divide by 2 to find out how many are above or below the median. Then it's just a counting game. So step 3, let's carry out the plan. First, we will need to calculate the total number of scores in the distribution. Adding the frequencies together, we're adding 3, 5, 7, 8, 11, 18, 12, and 9. That would be 73. The median is the score exactly in the middle of the distribution. 73 divided by 2 is 36.5. Thus, there are 36 scores below the median. The 37th score would be the median. And there are 36 more scores above the median in positions 38 through 73. Counting out, the first three scores are 1. Then 3 plus 5 is 8, so there are 8 scores, 2 or lower. Then 8 plus 7 is 15, so there are 15 scores, 3 or lower. We record these as the cumulative frequencies of the distribution. After we count the number of people that said 4 stores, after we count those 8, that's 23 scores that we have. After we add on the 11 people that say 5 stores, that's 34 responses that we have. And that brings us very close to 36 and a half. We had said that the median would be the 37th score. So that's going to be somewhere between the 34th score and the 52nd score. The 34th score is the last 5. The 52nd score is the last 6. So the median of this distribution must be 6, because scores 35 through 52 are all 6s. Very often, the median is paired with a range of the distribution. The range gives a measure to how far the distribution spreads out. We calculate the range by taking the difference of the largest data point, called the maximum, and the smallest data point, called the minimum of the distribution. In the last example, the maximum was 8 and the minimum was 1. So the range is 8 minus 1, or 7. Knowing the maximum and minimum, as well as the range, we can be somewhat more specific in describing a distribution. Half of the scores in a distribution are above the median and half are below, but all scores are above the minimum and below the maximum. So in the last example, we can say that half of the scores are between 1 and 6, and the other half are between 6 and 8. Now, when you look at your own score, you can determine if you are in the lower half or the upper half of scores. This is nice, but we can still do a little better. Looking at just the lower half of scores, we can split this group in half again. We can do the same with just the upper half of scores. Now we have the distribution split into 4 groups. We call these groups the 4 quartiles of the distribution. To define 4 regions, we will need 5 endpoints, which together are called the 5-number summary. Q sub 0 is the minimum score in the distribution. Q sub 1 would be the median of the lower half of the distribution, or the 25th percentile. Q sub 2 is the median of the entire distribution, or the 50th percentile. Q sub 3 is the median of the upper half of the distribution, or the 75th percentile. And Q sub 4 is the maximum score in the distribution. Scores in the first quartile fall between Q sub 0 and Q sub 1. Scores in the second quartile fall between Q sub 1 and Q sub 2. The third quartile is scores between Q sub 2 and Q sub 3. And the fourth quartile is between Q sub 3 and Q sub 4. Let's take a look at example 2 here. A group of students were presented with a page containing 30 colored rectangles. Their task was to name the colors as quickly as possible. Their times in seconds were recorded. The scores for 30 students are presented in the table below. Calculate the 5-number summary for this distribution. We have values 14 through 24. We have rows 2, 3, 4, 5, 6 of them with 5 numbers each. That is 30. So these are 30 scores. We want to calculate the 5-number summary. So we're well on our way to understanding the problem. Just to remind ourselves, the 5-number summary would be the minimum, the first quartile break, the median, the third quartile break, and the maximum. So let's devise a plan. Note that the scores are already presented in increasing order. We can quickly identify the minimum and the maximum. The median score is in the middle of the distribution, in this case, 15 scores below it and 15 scores above it. Once we have the median, we can use our strategies to look at the lower half and upper half separately to find the remaining values in the 5-number summary. So the minimum score, that's our smallest, that's 14. So 14 is Q sub 0. And the maximum score, that's our largest, that's 24. So 24 is Q sub 4. We can cut the distribution exactly in half so that we see 15 and 15. We see that 19 is the largest value in the first half. 19 is also the smallest value in the second half. So what do we have between 19 and 19? That's going to be 19. So Q sub 2 is 19. Looking at just the lower half, we have 15 scores here. 15 divided by 2 is 7.5. That means we're going to have 7 below and 7 above. And right in the middle is 17. So Q sub 1 is 17. Do the same just for the upper half. 7 below and 7 above. Right in between those sets of 7, we have our middle value of 20. So Q sub 3 is 20. Looking back at our result, together the 5-number summary for this distribution is 14, 17, 19, 20, and 24. What can we do with our 5-number summary? Well, we can make it visual with something called a box and whisker plot. A box and whisker plot uses the 5-number summary as a way of visualizing a distribution. Box and whisker plots are useful for identifying outliers and for comparing distributions. Let's graph the distribution from our last example on identifying colors as a box and whisker plot. We already have the 5-number summary, 14, 17, 19, 20, 24. We start with a number line to keep our scale consistent. Then above the number line, draw a box extending from the first quartile break, Q1, to the third quartile break, Q3. Mark the median, Q2, inside the box. So the box has to do with Q1, Q2, and Q3. The box extends from Q1 to Q3. That's 17 to 20. And Q2, 19, is marked in the middle of the box. This is the box of the box and whisker plot. Next, we put whiskers to the left and right to give additional information about the spread of the data. Whiskers are single horizontal lines extending out from the box that end in a vertical stroke on the minimum or maximum values in the distribution. So at the minimum of 14, Q sub 0, we have a vertical dash. At the maximum of 24, Q sub 4, we have a vertical dash. And then we just draw a line from the box out to the dashes. These are the whiskers of the box and whisker plot. At the beginning of this section, we claimed that quartile ranges are useful in comparing two distributions. To see how this works, consider a different group, this time of 36 students, whose performance on the color recognizing task is summarized in the following 5-number summary: 15, 19, 22.5, 25.5, and 30. We can draw a parallel box and whisker plot for this group's distribution above the box and whisker plot for the first group. Median, first quartile, third quartile, minimum, maximum, box around quartile 1 through quartile 3, whiskers out to the maximum and the minimum. Comparing these two box and whisker plots, we can see that most of the students in the second group took longer to identify colors than most of the students in the first group. However, the lowest times for both groups were nearly identical. Earlier, we claimed that a box and whisker plot is useful for identifying outlier data, individual scores that lie outside of where we expect the distribution to fall. Statisticians have not yet been able to agree on a single definition for what constitutes an outlier. We will focus on just one common definition of an outlier, called Tukey's fences. We start by calculating the interquartile range, that's IQR, and that's the width of the box in a box plot. In other words, the range just from quartile 1 to quartile 3. In our sample of 30 students' times in identifying colors, the IQR, the interquartile range, would be Q3 minus Q1, which was 20 minus 17, which gives us 3. The fences themselves fall a distance of 1.5 times the IQR above Q3 and below Q1. Any data that falls outside of this range is considered an outlier. In our sample, the upper fence would be Q3 plus 1.5 times IQR, which is 20 plus 1.5 times 3, which is 20 plus 4.5, which is 24.5. The lower fence would be Q1 minus 1.5 times the IQR, 17 minus 1.5 times 3, which is 17 minus 4.5, which is 12.5. So anything above 24.5 or below 12.5 in this particular case would be an outlier. But since all of our scores for this distribution fell between 14 and 24, there are no outliers in this distribution. Example 3. The following data represents the blood glucose level in milligrams per 100 milliliters after a 12-hour fast for a random sample of 44 women. So we have 44 samples. They are in increasing order. And we want to know, are any of the scores in this distribution outliers? So since we're given a list of data points in increasing order, and we're asked to identify outlier points, we will assume that outliers are defined by Tukey's fences. To identify the outliers, we need to use the interquartile range to calculate the positions of the upper and lower fences. And to find the interquartile range, we first need to calculate Q sub 1 and Q sub 3, which would be the endpoints of the box, or the 25th and 75th percentile ranks. So first we cut the distribution in half. We can see the median would be between 80 and 81, so 80.5, but we don't need Q2, we only need Q1 and Q3. So looking at the top half only, half is between 73 and 73, so Q sub 1 is 73. Looking at the top half, 85 and 85 are the middle values. Halfway between would be 85 again. So Q sub 3 is 85. From here, we can calculate the interquartile range, Q sub 3 minus Q sub 1. That's 85 minus 73, or 12. So IQR is 12 in this example. Now we can determine the position of the upper and lower fences. The upper fence would be Q sub 3 plus 1.5 times IQR. That's 85 plus 1.5 times 12, which is 85 plus 18, or 103. The lower fence, we're going down from the 25th percentile, so Q1 minus 1.5 times IQR. That's 73 minus 1.5 times 12, which is 73 minus 18, which is 55. So now we're going to look at the distribution and identify any scores larger than 103 and lower than 55. We don't have any below 55, so there's no low outliers. And we have one score above 103, so 109 is the only high outlier. Just as there is no one clear measure for identifying outlier data, there is even less agreement on what to do with scores that are identified as being outliers. Sometimes outliers represent errors in data collection, a miscalibrated experiment, or someone misunderstanding a question on a survey. When possible, double-checking the measurement of that data point never hurts. Other times, the outlier is a natural occurrence in sampling. It turns out that outliers should occur in slightly fewer than 1 in 100 data points using Tukey's fences. If your distribution has several outliers, all on one side of the median, that is a good sign that the distribution is skewed in that direction. All told, we take the approach here that outliers are points of interest in the distribution. Revisiting the data and asking what made that data point an outlier is usually an interesting question to explore for whatever the data is studying. That's section 4.2. Make sure you try the 4.2 homework before I see you again. Next time, we're going to go over the 4.1 and 4.2 homework.